All right, so today we're going to talk a little bit about the first law of thermodynamics and how it applies to simple processes. At the beginning of the Industrial Revolution, humans harnessed power using the first law of thermodynamics, and really before we could even understand it. So this photo here is actually a photo of a steam engine. It dates back to 1961. And so basically, what they did is they used steam, and the steam did work. And it's called a basic heat engine. So, what I want to talk to you guys about are heat engines, sort of to some degree. So, one of the most important things we could do with the heat engine is we can have a system, right? So, and I want to kind of just review the first law of thermodynamics real quick if I can, because this came up in the homework. Remember that the yellow part here, this circle right here, is the system. This stuff right here in yellow, the yellow circle, is the system, okay? So in general, the system, let me change that to transparent. We'll change the color. And so this part right here that's the system that we're talking about. So anything that goes into the system, anything coming into the system, going into the system would be positive. Going in would be a positive value. And anything coming out of the system would be a negative value, whether it's heat or work. And so keep that in mind as we move forward. But anyways, car engines and steam turbines, the kind that are used to generate electricity, are examples of simple heat engines. Heat's used to heat up the steam. The steam will move a turbine, the turbine spins, and work is done. This is a simple illustration of that where, and let me zoom in a little bit, or zoom out I should say, so you can see what I'm talking about. In this image, I have heat coming in, and I have heat coming out. So heat comes in, heat comes out, but also a little bit of work comes out. So in terms of the internal energy, the change in internal energy is kind of zero, and the work that's being done is actually the change in heat energy. So I have a certain number or value of heat coming into my system, and then as it leaves the system, we have to subtract it. So that's why this is a positive value and this is a negative value. And then the work being done actually leaves the system. So the work done by the system as opposed to work done on the system, because it's done by the system, it leaves. So that can have a negative value sometimes too, just to think about that. Okay, so what does that represent? Well, it's of course governed by the first law of thermodynamics, and it's impossible to devise a system where the heat going out is zero, right? Because no heat transfers, in which no heat transfers within the system. Like, you can't contain all the heat energy. You're gonna lose a little bit of heat energy somewhere. It's just not possible, okay? But now let's look at a piston, right? This is the most common one, like a car engine, okay? So a heat transfer on a car engine, basically you can have heat transfer into the gas in a cylinder, and it increases the internal energy of the gas, creating, and this is a steam engine, so we're talking about heat energy. Steam is a different thing too, but when you add heat into here, that increases the pressure of the gas, because the air molecules they're bouncing around, and when you heat it up, they vibrate more because you're adding heat energy into the system. And when they vibrate more, they bounce off this piston. Because the piston can move, it moves out. Well, how far does it move out? Well, it moves out the distance d, right? And then at some point, as the energy leaves, these molecules will cool off, kind of creates like a vacuum as the heat leaves, and then it goes back to the original position it was in before you added the heat. But now let's look at this in terms of work, okay? So we're adding heat, so up here, we're adding heat to the system. So energy goes into the system, we're adding heat Q. Right here, because of the excitement of the molecules, we're going to apply a force times the distance. Well, that's the very definition of work. That work is leaving the system. So it's negative. It's leaving the system. It's work done by the system. So it's leaving the system. The work being done is out here. Okay? So here we have a change in internal energy. We're going to add heat. That's going in. That's a plus sign. Here we're going to have another change in internal energy where work being done by the system leaves the system. And then as the heat leaves, the heat just leaves. All right? Now technically that's doing work into the system, because now we're doing work in the opposite direction, right? We have work going this way. So now we're putting work into the system, so to speak. And the force here, force prime, will be less than the original force. Well, why? Because we have to overcome friction. Okay, so that's how that works. We have to overcome friction. So we lose a little bit back and forth. So we have to keep adding heat, right? There's no such thing as a perpetual engine, heat engine or otherwise. So what does that mean? Well, if we look at this and we think about the volume and the pressure and the force and the cross-sectional area of what all takes place in the displacement of the piston, it would look sort of like this. And so the work going out of the system, right, this would be the work coming out if we push the piston up. That's going to be a force that's created on the inside. Where does this force come from? It's the pressure times the cross-sectional area, right? Well, where does that come from? Well, we can, this is kind of, if we push the piston down, right, we can increase the pressure, which creates a force. We can move the piston up, which decreases the pressure. So those are related. So then the work that goes out of the system is equal to the force times the displacement, right, over here d. Or you could think of it, because the force is equal to PA, the pressure times the cross-sectional area times the distance, which ironically, when you have the area, cross-sectional area times a distance, that's the same as the volume, right? So in this example, we have the cross-sectional area, which is of a circle. So I'm just going to write the formula in here. The cross-sectional area of the circle is pi r squared, right? Distance, if you want to think of it this way, distance over here is kind of like, well, I don't want to write it that way. Let's write it like this. If I take the area times, instead of saying distance, and I say that's the height that we move the piston. Well, if I say area times distance, that's the same as the area times the height. Well, that's going to be pi r squared times the height. Well, guess what? That's the volume. So whenever you have a cross-sectional area times a distance, that's actually the volume. So you can actually, where are we going with this? Well, I can calculate the work going out of a system if I know the pressure and the change in volume, okay? If I know the pressure and the change in volume, because you're going to start with initial, and let me highlight that too, the change in volume is equal to, just like everything else, the final volume minus the initial volume. So when this piston goes up or down, it changes the volume. So if I calculate the change in volume, that's how I'll get the work going out. Okay. And this, because the volume of the cylinder and its cross-sectional area, the A times the D, we would say technically, let me add this in here, I should write so there's no confusion. This is technically delta V, right? Because we can calculate the area of this right here. That's where I was going with that. So this is technically delta V, but instead of H, I'm just focusing on that distance. So what I'm really doing is I'm calculating the volume of the cylinder, and that's just the change in distance, right? That's what I'm really calculating. Which, if I were to make the volume of the big cylinder and then the smaller cylinder, now this works for what we call an isobaric process. What does isobaric process mean? Well, an isobaric process just basically means that there's no change in pressure. Pressure is constant. I'm going to run out of room here. So the pressure is constant. Okay. So what does that mean? Well, if I look at the graph of the pressure versus the pressure versus volume in this particular case, the work is the area under the curve, right? Because my pressure remains constant. Notice that there's no change in pressure, okay? That's a constant pressure. And then I have a change in volume, right? So we said that the work out of a system in an isobaric process is equal to the pressure, because it doesn't change, times the change in volume. Okay, so that's a simple engine. That's one particular scenario. Now, we can calculate this sometimes. Not everything is isobaric. See, this is just a regular rectangle when you think about it, right? I have a length times a length. And because the pressure doesn't change, and you could think of this almost like the length times width, where this is the length and this is the width. But now I don't know if you guys are aware of this or not, but you can actually calculate the area under the curve. This, but I'm not going to teach you that today. This is what calculus was kind of invented for. So you would take the integral of the function or in this case it would be P of V, right? The pressure as a function of the variable. And so what are you talking about, Mr. Adams? You could do calculus on this curve, right? Of P of V, oops, It still looks like an X. From V to V naught or VA, so you could say volume A to volume B, whatever that is. Okay? And so what that means is I'm just gonna, if you know calculus, you just calculate the area under the curve, and that tells you the work out. Okay? So this is actually more Calc 2, or at the high school level, this is more Calc BC. Calc 2 or Calc BC. And so when you, instead of doing this rectangle method, when you actually do Calc 2, you get that the work in should be the same as the work out. Now this is ideal, impossible. This is theoretical. You're going to lose some stuff. In other words, your work, because if you go back up to this image here, right, when you change the force, oh shoot, is it time for class? Let me pause this.